Throughout this video, we're going to do a desktop computer dissection using 3D animation, kind of like a dissection lab in biology class, but instead, we'll journey through the inside of this computer and disassemble every piece of hardware. We'll then use a microscope and zoom in to give you a nanoscopic view of the transistors and other structures inside. To make this video, we disassembled all the hardware inside a typical desktop computer. We desoldered and removed the components from each of the printed circuit boards and took thousands of pictures. Then, using these pictures, we meticulously 3D modeled every single component from the computer case down to the tiniest resistor. As a result, here's all the hardware that we'll explore throughout this video. It kind of looks like a crime scene where someone viciously destroyed a computer and arranged all the components. But anyways, let's dive right in. We'll begin this journey with the Central Processing Unit, or CPU, which is the brain of the computer. On top, we have the cover, called an integrated heat spreader, and inside is a smaller metal package that holds the integrated circuit, which is technically called a die. This die is mounted on a printed circuit board that distributes the 1200 connection points to landing pads that interface with the landing grid array on the motherboard. The integrated circuit inside has a few different sections, but perhaps the most recognizable are the 10 cores where programs and instructions are run. Each core is quite complicated, so here's a diagram laying out the different functional sections. There are dozens of rather complicated elements in this diagram, and you can look forward to a series of videos we're currently planning which will explore computer architecture and how each of these sections work. Let's zoom into a nanoscopic view of the integrated circuit so we can see individual transistors. These transistors are incredibly small, only a few nanometers wide, and in this die there are approximately 8 to 10 billion. On top of the transistors are multiple layers of metal wires, with vias rising vertically between the layers. Together, these transistors and wires create a multi-layer labyrinth or highway, resulting in a computer that can execute billions of operations every second. Let's now zoom out and look at other sections of the CPU. To the side of each core is the shared L3 memory cache and ring interconnect. On the far right is an integrated graphics processor which functions as a less powerful GPU. In the top left is the memory controller which sends data to and from the DRAM. And finally, on the far left is the system agent and platform I/O, which communicates with the chipset on the motherboard and manages the flow of data between many of the other components in your PC. So with that in mind, let's move on and look at the motherboard. This motherboard is a massive printed circuit board with thousands of wires running inside and a variety of microchips, components, sockets, ports, slots, headers, and connectors soldered to it. Perhaps the single most important and expensive component, aside from the bare PCB, is the chipset, which is this integrated circuit found underneath a heatsink down here and is connected directly to the system agent section in the CPU. Here's a diagram illustrating how the CPU and chipset are connected to everything else. As seen here, the CPU connects directly to the DRAM, one or two displays, the GPU, and perhaps a few SSDs plugged into the M2 slots. The chipset manages most everything else: data flowing through the Ethernet or Wi-Fi, data going to and from solid-state drives and hard drives plugged into the SATA ports, some of the PCIe slots, your keyboard and mouse, USB devices, and the audio sent to the speakers or from the microphone. Just a quick note. Computer hardware has evolved immensely over the past 65 years and continues to evolve. So the details we show should be thought of as a current-day example PC and not as how all computers work. Let's move on and skip over the many different sockets and connectors throughout the motherboard and focus on the voltage regulator module, or VRM, found near the CPU. These components are used to drop the voltage coming from the power supply down to the 1.3 volts used by the CPU. As a result of all the power flowing through these components and their 80 to 90% efficiency, heat sinks need to be placed on top. While we're on the topic of power, this CPU consumes power equivalent to approximately 16 LED bulbs, thus generating a considerable amount of heat, which is taken away by the CPU cooler. This particular cooler uses a pump to circulate liquid through these tubes and into the radiator's channels, which transfers heat to the radiator fins. The fans then help transfer the heat to the air, and the cooled liquid returns to the pump via the return loop. The pump is a brushless DC motor, constructed from a PCB, a control chip, and a stator on the dry side, a barrier in the middle, and then the permanent magnet rotor and impeller on the liquid side. There's no mechanical connection between the rotor and stator, thereby preventing any leaks of the cooling liquid. Let's move on to the power supply, which distributes power throughout the computer. In here, the main transformer reduces the voltage and bridges the isolation boundary between the primary side high voltage and the secondary side lower voltages used throughout your computer. Here's the control PCB that ensures a stable output voltage and sends adjustment signals to the switching power transistor on the primary side using opto-isolators. There are dozens of other components used to filter the input voltage and generate various output voltages, which are then sent to all the different hardware in your computer. For example, an SSD consumes just a few watts, and the connector uses these voltages, whereas your GPU can consume hundreds of watts using these connectors and these voltages. Next, we'll explore the GPU, but before that, let's take a step back and consider the technology we've covered thus far. Alone, each of these components doesn't do much at all, but when united, they combine to form a powerful system. Similarly, this video is a multidisciplinary combination of engineering, technology, art, and animation inspired by the Magic School Bus. We can't emphasize enough how important it is to be a multidisciplinary student. And to help you do that, the sponsor of this video is Brilliant.org. Brilliant is a multidisciplinary online education platform which teaches a ton of different topics in hands-on interactive ways. Here are 2 courses from different disciplines that you might think were entirely unrelated. However, when combined, they provide the foundational basis for a cutting-edge field of science and engineering. This combination of seemingly unrelated courses can be done with pretty much any 2 courses that Brilliant offers. Don't worry, you won't be learning from boring textbooks, but rather Brilliant uses interactive modules to make their lessons entertaining and help the concepts stick in your head. It's incredibly easy to sign up. Try out some of the lessons for free, and if you like them, which we're sure you will, you can sign up for an annual subscription. We personally are currently working through their lessons on quantum circuits and algorithms for a future video that dives into quantum computers. Brilliant is offering a free 30-day trial with access to all of their thousands of lessons. And to the viewers of this channel, Brilliant is offering 20% off an annual subscription to the first 200 people who sign up. Just go to brilliant.org/brancheducation. The link is in the description below. Let's get back to dissecting this computer and move on to the graphics card and GPU, which is also the brain of the computer. Well, actually, this analogy doesn't really work very well, but anyway. Opening the graphics card, we see another PCB with the GPU's integrated circuit in the center, VRAM chips all around, and the voltage regulator module on the side. Above the IC is a heatsink with a fan to dissipate heat, and on the side of the graphics card are HDMI and display ports, a PCIe interface, and then on the other side is the input power connector. Let's focus on the GPU integrated circuit, which, similar to the CPU, has more than 1,000 solder pads that connected to the PCB. Opening the packaging, we find the GPU die, which is noticeably different from the CPU. In here are approximately 11.8 billion transistors organized into 6 graphics processing clusters, totaling 28 streaming multiprocessors. Each streaming multiprocessor is composed of 128 cores, resulting in a total of 3,584 cores. Each core has sections for integer and floating point arithmetic, and sections for queuing in the operands and collecting the results, and is far simpler than a CPU core. Additionally, on the die is an L2 memory cache, shared among all the graphics processing clusters, a set of memory controllers that connect to the VRAM located around the processor, and a PCIe interface for connecting to the CPU. When we zoom in to see a nanoscopic view of the integrated circuit, we find something very similar to what we saw in the CPU, with the transistors on the bottom and a labyrinth of multiple layers of metal wires above. All these structures are manufactured in multi-billion-dollar semiconductor fabrication plants, or fabs, but that's a topic for a whole different video. So let's move on. GPUs and CPUs are similar in many ways. However, GPUs have thousands of cores that are limited to basic arithmetic, whereas CPUs have only a handful of cores that perform far more complicated operations. Additionally, CPUs have branch prediction and deep pipelines that optimize the execution of code. Here's a quick example of what GPUs can do. Take this image comprised of 16 million pixels, each with RGB values for each pixel. A simple way to brighten the image is to add 20 to each of these numbers. A CPU has 10 cores and thus performs arithmetic 10 numbers at a time, whereas GPUs distribute the data to thousands of cores, thus performing magnitudes more parallel processing. Let's close this graphics card and talk briefly about the 3D model. Note that this is a slightly older model graphics card because we buy most of our hardware as non-functioning parts from eBay, and then, as shown earlier, we tear them down rather destructively in order to accurately model everything. Additionally, sometimes components shown aren't compatible, such as this motherboard that says DDR4, while the DRAM is DDR5. That said, modeling and animating everything to make it feel like you're actually inside a computer took us around 500 hours, and we would greatly appreciate it if you could take a few seconds to hit that like button, subscribe if you haven't already, type up a quick comment below, and share this video with someone who will enjoy it. Also, we have a Patreon and would appreciate any support. We're planning more videos on computer architecture and other related topics, and can't do it without your help. So thank you for doing these 4 quick things. It helps a ton. Let's move on and look at the DRAM, solid-state drives, and hard drives. We're not going to spend too long because we have an entire series of videos on solid-state drives, and then separate videos covering DRAM and hard drives. But quickly, the CPU communicates directly with the DRAM through memory channels running inside the motherboard. Inside each of these 8 DRAM chips is an integrated circuit composed of 32 memory banks, each 8,192 columns wide by 65,536 rows tall. The DRAM temporarily stores data using capacitors and transistors called 1T, 1C memory cells in 2D arrays that look like this. Data can be accessed within nanoseconds. However, among these 8 chips, only 16 gigabytes of data can be temporarily stored. Take a look at our 35-minute video on DRAM. But for now, let's move on to SSDs, which permanently store data in 3D arrays called 3D NAND. This array is 100 to 200 layers tall, 32 to 64,000 columns wide, and 32 to 64,000 rows deep. Additionally, within a single SSD chip such as this one, are multiple 3D NAND arrays stacked one on top of the other. As a result, a single microchip can store terabytes of data. However, reading or writing data takes 50 or so microseconds, which is 3,000 times slower than DRAM. Zooming in on a single SSD memory cell, we find a charge trap which stores different levels of charge, allowing for 3 bits of data to be more permanently saved. Looking at the NVMe and SATA SSD, Both have a few 3D NAND data storage chips, a DRAM chip for buffering and holding the data mapping table, and a controller chip. Let's move on and dissect the hard disk drive. Here we have a disk mounted to a spindle with a motor that rotates the disk at thousands of RPM. A read-write head moves across the disk in order to access a single track out of 500,000 other data tracks. Let's zoom in on the read-write head. The write head changes the direction of localized magnetic domains in a small layer on the disk, whereas the read head senses these changes in magnetic domains. This disk drive is even slower than the SSD, taking a few milliseconds to access, thus resulting in slower read and write times, but costing less per terabyte of storage. Thus far, we've covered all the hardware inside your computer. So, thanks for watching this far. And as a bonus, here's what it looks like inside a computer mouse with the scroll wheel up top, the infrared light, image sensor, and multiple lenses down here, and the battery and processor in the middle. For computer mice, we have separate dedicated videos exploring the image sensor and scroll wheel with incredible details. Additionally, here's what it looks like inside a basic keyboard, with plastic traces that carry electricity to each key, and when pressed, that key completes a circuit which is sensed by the processor up here. That's pretty much it for what it looks like inside your computer. We believe the future will require a strong emphasis on engineering education, and we're thankful to all our Patreon and YouTube membership sponsors for supporting this dream. If you want to support us on YouTube memberships or Patreon, you can find the links in the description. Also, thank you again to Brilliant for sponsoring this video. This is Branch Education, and we create 3D animations that dive deep into the technology that drives our modern world. Watch another Branch video by clicking one of these cards, or click here to subscribe. Thanks for watching to the end.